Yes, certainly. Next topic of the speaker, Truong Tuyen, is a Newton method and connection to Schroder theorem, Voronoi's diagram, Newton's flows, and Riemann hypothesis. Please.
Okay, thank you very much for the opportunity to speak here, and yeah, thank you for me. So can I share my screen now? Okay, yeah, so then I can talk. So yeah, I changed the title because it's the other title is too long. Yeah, it's so it's I think it's very it's related to Voronoi, which I know who is Ukraine mathematician. So I think it's well. Okay, so this is the content of my talk. Uh, so I will yeah say about Riemann thesis and root finding for Riemann thesis, and then application of the a new root finding method, which is Bakhtaki-Newton method, and then I say about the equivalence and some experiments, and then some ideas how to use this for the Riemann hypothesis. And these are some references that I will use, and this one is the main one for the talk. And in this talk, I only talk about the Riemann zeta function, Riemann C function, but the ideas can be used for other zeta functions. And yeah, this. Okay, so we know that Riemann zeta function is originally defined by power series for real part of the complex number because one. But then we can also write such an integral, and then from that we can show that it has it can be extended as a meromorphic function on the whole plan with only one pole at one, and it's related to the gamma function. So if we define this Riemann C function like this, then we have this Poisson equation Cx equals C1 minus x, which allows us to show many things. For example, in particular, we can show that it has trivial zeros with -2, -4, and so on, which are related to gamma function. And then it's the other zeros, we call them non-trivial, and they are in the critical strip, 0 less than real part and less than equal 1. And actually, we can show that actually, if real part is 0 or 1, then we have no solution. Yeah, so it's strictly inside. And so yeah, so Riemann is well known. So it says that all known non-trivial zeros of zeta lies on the critical line, which is the real part of the complex number is 1/2, or it's the same as saying that all zeros of the C function lie on the critical line. And this has many applications and equivalence and connection to many fields like number theory, complex analysis, physics, algebraic geometry, and so on. For example, Wives Riemann thesis is well-known program, was a well-known program in algebraic geometry. And so this is one connection. So it's to the Laguerre polyar class. So it's we say an entire function is Laguerre polyar class if locally it can be locally uniformly approximated by polynomials with only real zeros. And so the Riemann hypothesis is equivalent to that the this function z maps to c 0.5 1/2 plus I z is of Laguerre polyar class. And we know many things about this. For example, we know that most of the non-trivial roots are very close to the critical line by Paul and Landau, or 41% of the non-trivial roots are simple by Bui, Conray, and Young. Or we know that if we consider the roots of the Riemann C function, the of derivative, mth derivative, then the density, the proportion of the numbers of zeros which on the critical line will tend to 1 when m go to infinity. This is resolved by Conray. But before that, Levison, he had some, he had first work on this. And also we have also experimental support. For example, till now we know that all the non-trivial roots of zeta with the imaginary part less than or equal 3 10 to 12 line on the critical line, Latin Tucson, and also Olisco has calculated many roots of very big height, like 10 to 20. And so because Riemann's hypothesis, it asked the question about the roots of manifold functions. So the one approach could be that we can use root finding method. So if we can have some methods to find all the roots, then and we can check it. Yeah. Or maybe that can help us can give us some insight. And so one, yeah. So this, so this one I just said, and so the experimental result that I mentioned before about checking that, for example, until 3 times 10 to 12, or the roots of the Riemann zeta, non-trivial root of Riemann zeta function lie on the critical line is they depend on, they kind of depends on the Turing method, and Turing method is a method which concentrates on the critical line. So it's just consider the restriction of the Riemann zeta or C function to the critical line, and it counts the number of roots on this critical line until some height, and it compares with the number which we get from using the argument principle, and if they're the same, then it means that we have all the roots on the critical line. So in particular, Turing's method cannot be used if Riemann hypothesis fails. If of course I believe that Riemann hypothesis will be true, but if it fails, then Turing method cannot find counter samples because Turing's method only uh, concentrates on the critical line, so it cannot find the roots outside of the critical line. Yeah, and then actually we know that there are some zeta functions where the Riemann hypothesis fails. For example, this is Davenport, there is a Davenport-Hell-Brown function, and also there are many other functions, but yeah. Also, there's some phenomenon in phenomena in analytic number theory that some conjecture may be true up to a very high number, but actually they are not true. Yeah, for example, skews number, which you can see on the on Wikipedia. So now, okay, so now I consider root methods, root finding methods, which can find roots in the complex plan, not only on the critical line. And one of the famous methods is Newton method. And it's like this. So for example, f set is a manifold function, and we want to find roots of it. So we have set n plus 1 equals set n minus f set n over f derivative set n. And we choose a random initial point z0, and we consider this sequence. And we hope that this sequence will converge to a root of f. And a typical example is if we want to find an nth root of a number a, then we apply Newton's method to this function z set n minus a. And this is the formula we get in this case. And this method is very attractive because it's fast. If we are close to a non non degenerate root, then it has a array of convergence quadratic, and it's extensively researched, and not just in one variable, but in many variables, and many good results are known. But however, it has no global convergence. For example, Macmullen showed that if we look at the polymers of degree 4 or more, Reddick polymer, then it's the method doesn't converge, doesn't have guarantee to converge. And beside that, it may have strange attractors, so maybe it can have attracting periodic cycles, which are not roots or not critical points also. And it's also chaotic, so I will show you what does it mean. Okay, here. So this is the pictures of Bayesian attraction of Newton method. For example, this is a very simple function, say 3 plus 2. And so we have three roots here. You can see one here, the dot, yeah, the dot here. And then for example, if you have an initial point z0 of green color, so you use Newton method if you convert to this root. And if you use this, I think it's yellow. So yellow points if you convert here, and this one I think it's brown or something. And it will convert to this root. And the thing is not, it's very fractal here. So for example, you cannot guess what happens if you are on this domain in the near the boundary, because it's you can see something like red, but it close to that you can see and then the red points are the points that not converge to any of these roots, so you have some points would not converge. And also you can see that some green domain, and they very close to um, yellow domains and so on, so very fractal. So basically it means that you cannot guess what if you choose a random point here, you don't know where it will go. So that's not good thing of Newton's method. Let me see. So now I come back to my slides. So then there's some variants. So example one is called the relaxed Newton method, which is like you add an alpha here. Instead of one, you add alpha. Alpha is a complex number. So it has the same issue as Newton method. Um, and what happens is that if you choose alpha very small, then it might be related to this Newton flow. And Newton flow is better. Um, however, the thing is that alpha, this only is proven for f is a rational function. So it's a quotient of two polynomials. And also if alpha very small, then if you use it in practice, it's very slow. Yeah. Another one is a random relaxed Newton method, which instead of alpha fixed, you put alpha n. And then alpha n you choose randomly in one of such domain like this. Alpha minus 1 absolute value less than rho, and rho is a constant between 0.5 and 1. And Sumi show that if you fix the point z0 and you fix the polynomial, then for almost all choices of such sequence alpha n, then this sequence zn will converge to a root of f. So basically, this says that random relaxed Newton method is a good method to find roots for polynomials, but we don't know what it can do for multiple functions like Riemann's zeta or Riemann C functions. Yeah, and also the result that are proved here, for example, for a Newton flow, Newton relax, or random relax Newton, they're not known not yet extended to higher dimensions. Now, now we can also find a root of a function by using optimization. So how can we do this? Um, First, okay, I will tell about Newton method for optimization, which is related to Newton method to find root. So for example, we have function f from real number to real numbers, and we want to find local minima of this function. So okay, so we know that local minima or critical points of f, which is the roots of f prime. So if we apply this method to this f prime to find critical points, so this is what we get. Yeah, we xn plus 1 equals xn minus f second derivative xn minus 1 times f derivative xn. And this formula can be extended to a higher dimension by in higher dimension you have f from Rm to R. Then you take the Hessian, you replace the second derivative by the Hessian matrix and the derivative by the gradient, and you have the same formula like this. So this is Newton method for optimization. And in this talk, we will be concentrated in m equals 2 because we will work on C, and C is R2. And again, this one is again it has near non-dependent local minima. It has the same rate of convergence like the Newton method for root finding, and also it's also easy to implement in computers. But again, it has no global convergence guarantee because every critical point of this function f may be can be abducted. I will show you one picture like this. Let me see. Maybe this one. Let's see. Maybe this one. Yeah, this one may be better. No, maybe this one. Sorry. Okay. Let me show you. Yeah, so this is a picture. And you can see that so this is a picture of a polynomial with three roots. Okay, I open this picture. Three roots, polynomial degree 3. And this is what you get if you apply Newton method for optimization. This is what you get. The okay. Yeah, the second row and the first picture on the second row. So it's the picture you get for if you use optimization for or Newton method for optimization. And you see that it has plug points, which are the points where it's not converts to one of the roots. So yeah, three roots. And what happens to that is that okay, this degree 3 polymer. So you have two critical points, and actually the plug points are attractors to they are attracted to the two critical points. Yeah. So basically, in general, they can this method can apply to all yeah has no global convergence. And by the way, the second picture on this um on the second row is the picture you get for the method Patrick Newton method BNQN, and it can find all the rows. You see no plug points, yeah, and it's you see that it's very smooth, yeah. And I come back here. Yes. Yeah. So then how can we find root of f of manifold function f? So we look at fx plus y squared, absolute value, and then if we have root, so it means that it's the function, the capital F is always non-negative, and if it's 0, then it's the global minima. So if we can find global minima of functions, then we can find roots. And so we can apply new possible Newton method for optimization to find roots of manifold function f by applying it to absolute value square. But as I said, Newton method for optimization is still not has good global convergence guarantees. Now I present this method, new method BNQN. Yeah. So so in general, so if we have an algorithm, so what we want for finding local minima. So first, we want so we construct some sequence set n plus one by applying our method, which I call IM, to set n, and then we want convergence. We want the sequence to converge, either converge or go to infinity. And the second one is that if it converts to a point z star, or even if it has a subsequence that converts, then z star should be a critical point of f, because we look for local minima, so and then local minima are critical points. And then second, and then how can but we have many types of critical points, and then one which might be troublesome is that saddle points. And so we want to avoid such points. So we want that if z0 is randomly chosen, then z9 is not saddle point. Then roughly speaking, so these criteria will assure that we can find local minima. Yeah. And by the way, so in optimization literature, so usually people assume that many several strong converge conditions, for example, convexity or uh, derivatives are Lipschitz continuous, but this does not apply to Riemann C function. And how can we do this? So if we look, so what's the idea? So we just look at this function f x y equal x squared minus y squared. So it has a set point at 0, 0. And so if we have a good method, so it should avoid this 0, 0 point. But if we apply Newton method for optimization, then you can calculate that actually you start from any point, and then the next point will be 0, 0. So it's not good. So how can we do this? What we can do is that, okay, we observe that at this point, then the Hessian matrix, it has an eigenvalue of negative with a negative with a minus 2. And so how can we go away from this? The idea is to change this minus 2 to 2. This is, yeah, so instead of Hessian is 2, 0, 0 minus 2, I replace it by 2, 0, 0, 2. And then you calculate, and then you see that the next point not 0, 0, but it's 0, 2, y0. So except if y0 is 0, then it will go away from the settle point like we want. And this yeah, this is one of the ideas for this method. And so in this paper, try with other correlators, so yeah we use this idea of changing the eigenvalues, negative eigenvalues, but we also need to add a correction to the Hessian, because this it has two purposes. So first, it avoids the case where if the Hessian is not invertible, so you cannot take the inverse. So you add this in, and so it will be invertible. But the more important thing is that you add this in, and then it will allow you to avoid certain points. Yeah, you can prove that you will avoid certain points. If you don't add, then I don't know how to prove this. Even though I think that it will be true for in general, because I did many experiments and it seems so. And this delta here is you can fix from beginnings a set with m plus one variables numbers, and m is the, the the dimension of your problem. And yeah, so it's very simple to do it. And then yeah, so this is the theorem from this paper, which show that if you choose this m plus one numbers randomly, then you can avoid settle points. And also still you have local rates of good local rate of convergence, but it's not have global convergence, because if you start from some z0, maybe it not converts to uh, a local minimum, or and also it not go to infinity, so it may go to somewhere else. So then in this preprint, I modify the definition in some aspects, and more importantly, I add this so-called Amizo-Baktakin license to assure global convergence. And so what is this Amizo-Baktakin license? So actually, it's very simple. So if you have some W, vector W with the inner product is strictly positive at this point set, and you can always find a positive number gamma, so that fx gamma W minus fx less than or minus gamma W, and gradient divided by 3. And then backtracking, because you can choose gamma from 1, and then you decrease it to 1/2 to 1/4 until this inequality is satisfied. So this why it's called backtracking. And then with this backtracking thing, then I can prove that we have this everything we want. And more importantly, for finding roots and manifold function, then it's very good that if the sequence we constructed, it has a bounded subsequence, then if you convert to a point in C, and this is the root of f or root of f derivative. And secondly, if fz is standard in the sense that this f and f second derivative has no common root with f derivative, then either then this z star will be a root. Yeah, it's not a root. It's the root of f and not a root of f derivative. So the point is, because in this case a root of f derivative will be a saddle point of the function capital F, and we know that we can avoid the saddle point, so we don't have this issue. Yeah. And here is the algorithm. Just like what I said. So the first if and n is to choose the delta. We add in the correction for the Hessian matrix, and the 3 or 4 lines in between is next is to change the size of the negative eigenvalues, and the last one, the while do is to check the Amizo condition. And then okay, now I will say about the application to Riemann hypothesis. So first, we have a new equivalence to Riemann hypothesis. So if the Riemann hypothesis is true, if and only if the BNQN apply to C square, all attractors of BNQN lie on the critical line. And the statement 3 is that BNQN, then for any Z0, then the Zn either go to the line, critical line, or it's go to infinity. And here is explained an attractor just means that a point, and then you have, or actually more generally, come back to set K, so that you have a neighborhood, open neighborhood yield, which will be constructed by K under the iteration of your dynamics, your method, and in this case, it's BNQN. And then we can show that any root of C, of the Riemann C function, is an attractor. And then if we know if Riemann hypothesis is true, then all of the C is poly R Lagrange poly R class, and the derivative also. And so the roots of C and C prime are all on the critical line. So then then we can show that Zn will converge to, because Zn will converge to a root of C or C prime, so it must converge to the critical line. And this theorem 5 is it show that this BNQN it can be a good root finding method for C. If we assume that Riemann with its holds, and we assume that the zeros of C and C prime are or simple, which seem to be the case from the partial results so far. And then assume the parameters randomly chosen. Then and if Z0 is randomly chosen, then Zn will either converge to a root of C or it goes to infinity. And now I come to the application of Voronoi diagram to this Riemann function. So in this paper, we observe that there's some similarity between the Bayesian notation being given and Newton flow and Voronoi diagram. So I won't say about Newton flow, but we'll say about Voronoi diagram. So let me come to this. So Voronoi diagram. Okay, let me just close this. Yeah, Voronoi diagram. So Voronoi diagram is like this. So you have maybe discrete set of points on the C, and then Voronoi cell just the set of points on this C which are close to this point. For example, yeah, and then you roll and the boundary curves are lines, yeah, line segments like this. And Voronoi diagram, you can see it on possible and giraffe skin. So now let me come to this paper. Yeah, so first of all, this is polynomial 3. And the first picture on the first row, you see is the Voronoi diagram for the set of three roots. And then the second picture on the second row is for P and QN. And you see that, yeah, looks very similar. And also the second picture on the third row, third row is for Newton's flow for P over P prime. Yeah. So the three looks very similar. So that's what I mean. Okay. So let me come back to uh, uh, yeah, maybe this paper. So what happens if you have all the in the case of Riemann hypothesis, if it's true, then all the roots are on the critical lines. So so then what you see the first picture on the first row here, you see the Voronoi diagram for the first 8 roots of the Riemann zeta function, and you see there are lines which are parallel to the x-axis. Yeah. So in particular, each of them will intersect the y-axis in a non-empty open set. And the first picture on the third line is what you see when you use the BNQN for polynomial of degree 8 with the whole roots are these eight roots of Riemann C function. And you see very similar. Yeah.
5 minutes, please.
Yeah, okay. Yeah. So yes. So it means that if this similarities is correct, and actually it's proved for degree 2 in this paper, then it means that we can find roots of Riemann C function by starting from Z0 on the x-axis and on the y-axis, sorry. And y is good because we know, yeah. So this one I wrote here. And actually we check it. That's actually we can find. For example, in this paper, we check it for very big numbers like this. We try to find those where y0 is between 10 to 9 to 10 9 plus 1. And we found that we can find all these roots by looking points on the y-axis. and with 0 y0 and y0 between 10 to 9 minus 1 and 10 to 9 plus 1 by B and Q. And then yeah, so and then we also found many other observations possible. We found that if we start from a point z0 equals 0, 0, 0, y0, then we need about O of log y0 iteration by B and Q to go to close to the critical line. And it can find all roots of C. And it seems that the sequence doesn't, if I start with this just points, then it's not converts to infinity. So it means that it will converge to either root or a root of C or a root of C prime. Yeah. And so then it um, suggests some ideas to the Riemann hypothesis. So to solve the Riemann hypothesis, and this is I wrote here. And so first to show that there's some the similarities between Voronoi diagram and B and Qn, we can prove it for the Riemann C function. Secondly, we show that if we have 0 y0 in this subpoint and we need about z o log y0, uh, and zn, yeah, O of zn will be uh, bounded by this. And so it means that they don't go to infinity, so they must go to a root of C or root of C prime. And then we show that uh, uh, after iteration, O log y0 iteration, they go to special points of the Newton method called the counter-Lewis or Smell collisions. And these are very good points, yeah, because we know then they will converge to a root of C. And then we saw that BNQN and Newton method will converge to the same point from this point that we stop here. Yeah. Yes. So this the ideas. Yeah. And and if we can prove all these, then we can prove the Riemann hypothesis. And it's we found that to prove the similarity between the BNQN and Voronoi diagram, then the ambiguous condition, which I saw before, is was very important to for degree two polynomial. So maybe it's also for C function. And yeah, so thank you. And yeah, also maybe we need to estimate better the Riemann C function than the result we have now. Yeah. So yeah, so that's the end. Yeah, thank you.
Okay, thank you very much for a very interesting talk. I would like to ask one question, please.
Okay.
You considered the method of the solution of equations with complex or real coordinates, but what about multidimensional space? Can you
Yeah,
consider
okay.
4-dimensional, 5-dimensional, and so on?
Yeah, it's this method it can be applied to any dimension. And I also yeah, maybe I open the paper this uh, yeah, so let me open this paper
Mhm.
okay. So yes, let me see. Yeah, so this
Number.
paper where I define this method, and it's applied to yeah, any dimension. And for example, for optimization, then it can avoid certain points, and it can convert. It has convergence for example, if you have polynomial equation with some condition like this, then
Mhm.
I can prove convergence. Yeah, um, I can prove convergence. Yeah, yeah,
Okay.
yeah.
Uh,
So you can apply to any dimension. And
and
this in this case for Riemann C function, so we apply to dimension two. Yeah.
And archive number, can you say me the number of
What
this
you say?
paper? The number of this paper, archive number.
Oh yeah, okay. So it's here. 2209.05378. Yeah.
Okay, thank you very much.
Yeah, okay.